address you during the SaGHAA conference. What I want to do is to share some new results and encouragement to you all about some data we have open for sharing. And I have this. Okay. The Arctic, as we heard earlier today, is changing very rapidly, and many of us are today talking about a new Arctic regime change. And we are also seeing that this aerial extent of the Arctic sea ice is changing, diminishing, and today, during the last about 10 years, the summer sea ice cover in the Arctic is covering about 40 to 50% of the area. And we see that there is a decline of about 13.2% per decade in the aerial cover. It's not only the cover of the aerial coverage of the sea ice is changing, but we are seeing also that the thickness of the sea ice is changing, such that from a multi-year ice that was 5 to 6 meters thick, today we see there's very little of that ice is preserved, and it's these white areas, and we see that they are only restricted to the northern parts of the Canadian archipelago, whereas most of the Arctic Ocean is covered with 1 year or 2 year sea ice about 1.5 to 2 meters thick. So the ice is really changing in the Arctic. And the recent assessment on snow, water, ice, and permafrost in the Arctic, the SaGHAA report by the Arctic Council is saying that by the end of 2030, the summer Arctic will be sea ice free. So we have a number of questions which we need to address regarding the Arctic that is going to be in the future, the changing Arctic. And these questions are: what melts the ice? Is it the Atlantic water beneath the ice, or is it the atmosphere above the ice? And how is that balanced? How does the thinner ice respond to atmospheric forcing, such as storms? How does thinner ice affect ice dynamics? And how can we improve ice drift models? What are the effects of the changed sea ice system on the ice-associated ecosystem? What are the effects on local and global weather systems of the Arctic? And all this knowledge and more is actually needed to improve our computer models to predict the future conditions more accurately. And in order to address some of these questions, the Norwegian Polar Institute in the winter of 2015 organized a half-year, 6-month-long expedition to the area, the sea ice area north of Svalbard. And one of the major issues we wanted to address is, one, looking at winter conditions. Usually when we are out in the field is during the summer, but we also need how things evolve through a whole year cycle. So we wanted to start with the winter and look at the parameters, the changes of the first year ice, the thin ice in this area. And as you can see, this is Lance, our previous ship frozen into the ice during winter. So the scientists were also looking at the coupling between the atmosphere, the ocean, the ice, and the ecosystem during this whole cruise. And the boat we had 4 separate drifts where we continuously collected data from the atmosphere, the ice, and the ocean, and the ecosystem. And we invited also many institutes to participate, international and national, to this expedition. We had 32 researchers from 15 different international institutes covering 10 countries. So it was quite a fun international collaboration. And here comes perhaps one of my most important slides for you, because all the data we gathered during this 5.5-month expedition, they are becoming available on our database. So at present, there is over 15 or 18 data available for anyone to be able to access them. So I would urge you, if you are interested, look at the data. Do contact my colleagues, because you do need to have some background information to be able to use the data, but the data is freely available. So do look into the database. There is the website for the database, and if you go to the website of the Norwegian Polar Institute and click on the NICE logo, you will see both a link to the database, but you will also find a link to our publications. So all publications that are coming out of this research or the expedition are also available on our website. So what I'm going to do is, and okay, I have to remember to say one more thing, that we are also collecting all the publications in a special issue of Journal of Geophysical Research, in addition to that scientists are publishing their data or research in different journals, but all of that you can have access from our website. So I will try to give you some very briefly main findings and the details of this, because this is a very comprehensive expedition you will find in the publications on our webpage. So what we saw was that the ice pack had already, during the January, accumulated nearly 0.5 meter of snow. This is much more than we expected based on climatology. And the thick snow cover slowed, therefore, the sea ice growth. And ice formed mainly in leads, and the thick, heavy snow also contributed positively to the ice mass balance through snow-ice formation. And you can already see the heat coming from the ocean. Many storms took place, especially in winter, which is a new phenomenon in the Arctic. And these brought with them warm and moist air, even in the middle of the polar night, also slowing ice growth. These storms, they also affected ocean mixing. Heat, nutrients, and CO2 were mixed throughout the upper water column during storms, and we saw the ocean heat flux increase twofold during storms. The thinner sea ice was, since it's thinner, more easily broken up by these storms, and we also observed more ridging and lead formation than previously. And leads caused by storms also allowed enough light to reach the water, sufficient to initiate and maintain an algae bloom. Under thick snow-covered ice, which was a surprise for many of us, that otherwise would have kept the algae community in the dark and unable to grow. The heavy snow load also resulted in seawater infiltration at the snow-ice interface, which provided a habitat that supported ample algae growth, resembling conditions in the Antarctic sea ice zone. These are just for you to have access to later on the main a summary of the main findings. Now, what we are seeing is that the Arctic is warming more rapidly than the rest of the world, and the decreasing or the narrowing temperature difference between the Arctic and the lower latitudes is weakening the speed at which the jet stream circumnavigates the Earth, and it's also thought to be making the jet stream more wavier. And we're also seeing that the global warming is increasing the strength of hurricanes, and this is something we also observed during this expedition, the winter hurricanes. And we know that the atmosphere holds more water vapor, and sea surface temperatures are rising, and both of these changes strengthen hurricanes. Cyclonic activity plays a prominent role for the warming of the Svalbard region. We are seeing in the Arctic one of the areas that are warming strongest is actually the Svalbard area. And it's affecting also the atmospheric, terrestrial, and marine subsystems. And my last slide. As we can see here, the wavier jet stream is causing the cold air masses from the Arctic to penetrate much further south. That's why we call it Arctic effect on mid-latitudes. But we are also seeing that warmer air, as in the case of Svalbard, is penetrating further north into the Arctic, mid-latitude effect on the Arctic. And as the Arctic keeps warming, the jet stream is expected to become even more distorted, bringing ever more heat and moisture into the Arctic. And this constitutes a self-reinforcing feedback loop that keeps making the situation worse. So as the Arctic is changing this dramatically, we also have to understand how this is going to affect other regions of the globe. And here we have also already heard that there are many of you who are looking into this topic and trying to understand the effects of Arctic changing to the monsoon systems in India. Thank you.